Hello everyone, welcome to Environmental Point Clouds, some basic concepts and applications of Lidar. This is part of the Lidar workshop organized by the University of Rennes and the University of Potsdam. And in the next couple of hours, we are going to talk about point clouds, structure for motion, and some other topics. This recording here is intended to be fairly dense and is providing a lot of information in a short time. And the idea is that we are going to meet afterwards and discuss some of those points in more detail. The idea for today is to talk about some spatial terminology, raster and gridded data, point clouds and voxel grids. What are those and how can we use those and why are they important? We are going to talk about characteristics of LiDAR data, some uh, ideas of how we can generate points from full waveform LiDAR, and we are going to walk through an example there. And last but not least, some examples and applications from previous publications. I also would like to point out that there is a second part of this class that focuses on stereophotogrammetry, and there we talk about stereo vision and generating point clouds from overlapping imagery. That is a fundamentally different way of generating point clouds, but has a wide range of applications. So we are going to talk about some structure for motion and camera orientation and location problems. We use structure for motion to solve for camera orientation, camera calibration, and the camera location. And we are going to talk about how we can generate dense point clouds by using disparity or depth maps. And this is followed by some examples and applications. So this is a accompanying lecture that will take place in an hour or two or so. So let's zoom into some spatial terminology that we will be using throughout that entire course, and it will be important to familiarize yourself with those terms because we will be using them in the programming exercises as well. Raster. Raster primarily refers to a characteristic of a data structure, that is, a two-dimensional or a multi-dimensional array. In NumPy or in MATLAB, you are familiar with arrays or matrices. A raster is a representation of such a raster. Pretty much every satellite or air photo is raster data of a surface. This, is a very common example of raster data. Raster data can be projected onto an equally spaced grid. And if you have an equally spaced grid, you often refer to these data as gridded data. So generally, gridded data refer to equal distances between grid cells in a raster data structure. So for example, a digital elevation model, a digital terrain model, an orthophoto, these are examples of a gridded data set. Gridded data are rasters, but not all rasters are grids, meaning that rasters is a larger group of those two. As an example here, on the left-hand side, we have an old analog air photo that has not been orthorestified, and if you look at it closely, you clearly see distortions in it, and you have a raster data set. On the right-hand side is a gridded data set derived from hyperspectral data. This is an NDVI data set that has been corrected with airborne LiDAR data, so we have a very precise information of elevation, and that allows us to undistort this image and turn it into a grid. This is, by the way, the Castle Sanssouci, one of those famous buildings that has been reproduced after that building in Paris. Points. Point clouds are fundamentally different structures. Here you see a view of a point cloud from an area that has been heavily influenced by erosion, and you can see the individual points here that make up the structure. So this is neither a raster nor a gridded data set and contains a different set of information. So point clouds are Cartesian coordinates, usually x, y, z, but they often also have additional attributes. So you can have additional attributes of spectral information, laser pulse metrics, neighborhood informations, or other parameters. And you can create n-dimensional point clouds. Point clouds can be stored in various data types, and they are also organized and structured in a very different way than arrays or grids. Here's an example of a point cloud using different attributes. This is showing the flow accumulation on a point cloud, where the coloring indicates the number of upstream pixels, something that we are very familiar with from gridded data sets. We will be covering this at some later point today and in the coming weeks. The distances between points vary, and several assumptions that we usually have in gridded data sets are not valid. If you have a time series of point clouds, if you have, for example, a point cloud from a pre and post event, then you need to align them. You probably have to homogenize them because they may have different spatial resolutions, or you need to do other processing steps before you can actually do the analysis. And that point cloud alignment is a big part of this class and this course, and we are going to look at that with a couple of examples later this afternoon. Voxels are a way of aggregating points. So you can create kind of a gridded data set for points by voxelizing the data. Voxels are n-dimensional grids, but mostly we use three-dimensional grids, and they have regular grid size. They have regular sites in each direction, so we are creating cubes. Typical example here is a voxelized point cloud for a river pebble data set that reminds you very much of a Minecraft data set. This is in a resolution of 1 millimeter. We can, of course, change the voxel resolution where we can have larger voxels and therefore aggregate more data into a somewhat coarser structure. In this next part, I would like to talk about some characteristics of LiDAR data. And I'm starting out by giving you some thoughts about what LiDAR is. LiDAR is an active remote sensing technique, meaning that you have a sensor that emits the signal and can also receive the return signal. This is fundamentally different to passive systems such as Landsat or Sentinel-2. Active sensors are often more complex than passive sensors, but they also give you more opportunities to observe and record data. Examples of active remote sensing instruments are radar, which stands for radio detection and ranging. These are wavelengths that are significantly longer than the optical visible wavelengths. Lidar, light detection and ranging. This measures the time of a laser pulse, usually in the visible or near infrared part of the spectrum. And you may be familiar with sonar, which is sound navigating and ranging. That is often used for bathymetric observations. The basic principle of LiDAR is that you are measuring distances through a very, very precise time. So you can envision that you are sending off a pulse, a laser pulse that hits an object, gets reflected, and the detector records the timing of that returned wavelength. So we can measure the time difference of a specific point, for example, of a peak. And because we know the velocity of light, we can change that, or we can convert that into a distance. This is what we refer to as a time of flight measurement, or TOF. This is the most widely used way of measuring LiDAR distances, but it's not the only way of measuring LiDAR distances. An alternative way of measuring LiDAR distances that has become fairly common in the last couple of years is exploiting phase delay measurement. That means that you envision the oscillating wave of that wavelengths, for example, the 1064 nanometer wavelength, and you can measure the phase offset within that wave to have a much more precise distance measurement. This is somewhat similar to radar interferometry, where you're looking at the phase offset between an outgoing and a return signal. Some newer generation models, LiDAR models that combine these approaches. For now, most of these are only used in terrestrial LiDAR systems. A couple of comments here. The time of flight distance measurements usually has centimeter to decimeter accuracy. And the largest uncertainty is the airplane position itself. It is not the laser timing measurements. That usually is fairly precise, but the location of the airplane needs to know to turn it into a continuous data set. And there, the problem often is that the GNSS measurements or the GPS measurements have a lower sampling frequency here. With common sampling frequency is 5 Hertz, whereas 5 Hertz, whereas a second device that tries to identify motion on that LiDAR airplane, an inertial measurement unit, has a much higher frequency of sampling. The combination of those improves the location measurements, but certainly additional improvements are necessary here. If you want to achieve sub-centimeter or millimeter accuracy, you usually go to phase shift or coherence patterns measurements that I just talked about. Another comment that I wanted to make here is that for topographic surveys, we only rely on pulsed laser systems. These are repetition rates of roughly 100 kilohertz, or the newer models 1 megahertz, which means that you're sending off a million points per second, and you're measuring a million points per second being returned. That's quite a dense point cloud that you can generate this way, and these are the modern systems that exist. A comment here regarding the beam divergence. We have common beam divergences, so how the beam is opening up as it goes along a certain distance of 0.3 millirad. That usually gives you a footprint of 0.3 meters or 30 centimeters at 1,000 meter flight height. So these are modern systems that allow you to have a fairly small dot on the surface. In terms of lasers, in terms of generating these data, the most commonly used LiDAR system is a synthetic garnet in neodymium-doped yttrium aluminum garnet, and that generates the 1064 nanometer wavelengths. If you apply a frequency filter, you can obtain half of the wavelengths at 532 nanometer. That is often used for bathymetric applications. So these are two very common wavelengths that are being generated with the same device. Okay, let's talk a little bit about some main characteristics of LiDAR systems. And I'm talking mostly about 4 points here, and I'm making the assumption that you have an airplane as being part of an airborne LiDAR system. So we have a laser, we have a GPS GNSS system that allows us to get precise absolute locations, and we often have an IMU, an inertial measurement unit, that allows us to measure acceleration, deceleration, rotation, and other moving components. And we need a computer storage system that allows us to store the collected points. Think about that if you have a million points that are being, or a million wavelengths that are being returned each second, you need to have a very high throughput system that allows you to store these data sets. Just a few quick notes regarding the laser setup. Lasers or LiDAR contains the aberration laser, and laser stands for light amplification by stimulated emission of radiation. As pointed out before, the neodymium yttrium aluminum garnet is a commonly used synthetic mineral. And it also emits in some other wavelengths that are used for other applications, but the 1064 nanometer is also the highest energy component that is being sent off by this device. Laser light has 4 unique characteristics, and those 4 unique characteristics made LiDAR observations possible. So in the past 2 decades, there have been made significant advances in laser technologies, but the core concepts remain the same. So laser light is fundamentally different from ordinary light. We have a coherence light, meaning that all the emitted wavelengths are in phase. They have a high directionality. That means there is not much beam divergence. All the emitted light has the same wavelength. This is a very important point because this allows us to better understand the reflective properties of an object. And the high coherence directionality, the high monochromacity gives us a high intensity, which is what we need if we want to send off that laser beam over a longer distance. Let's talk a little bit about some system specifics. So we just referred to the unique properties of a laser. And I would like to talk more about the beam divergence, scanning angle, scanning frequency, and the scanning pattern. These are different between different missions, or they can be different between different missions, and it is important to familiarize yourself with those to understand what the data concept is. Beam divergence is a very important point because it tells you what the size of the footprint is on the surface. When you look at point cloud data, you only have a single point that can be very, very, very small, or infinitesimally small in that sense in an XYZ coordinate system. But the actual data are being generated from a much wider beam. So it's important to understand that the points that you're looking at are actually derived from a beam that has some width. Common beam divergence of 0.3 millirad result in a 30 centimeter footprint at a 1,000 meter flight height. If you go up to 2,000 meter flight height, you have a roughly 0.6 meter high footprint. So these are common concepts. You can determine the footprint with yourself. You can look up the beam divergence in the technical spreadsheet of every manufacturer. Common is 0.3 or 0.1, and you know the flight height, or you know the distance to the object, and by using a simple geometric relation, you end up getting the width of your footprint of the LiDAR beam when hitting an object. This is important because we have small and large footprint systems. In most of the cases, most modern LiDAR systems use a small footprint system because they want to have a very precise measurement of a very small distance. But for many applications, specifically vegetation applications or vegetation LiDAR applications in ecology, they rely on large footprint systems that have on purpose a larger beam divergence because that allows you to better penetrate through vegetation. So this is very important when you are interested in biomass estimation. So this is something to keep in mind, that you need to look at the width of that point that you're working with, and these can be derived from the technical information of every LiDAR system. Scan angle is another important component. You know that the LiDAR, that you have a rotating mirror that is diverging the beam across your transport or flight direction. And usually you have a scan angle of 60 degrees. Some newer devices even have a wider scan angle, which means roughly plus minus 30 degrees from nadir directly below your flight direction. Or often you end up only using plus minus 20 degrees, but you are often collecting additional data. So this gives you the overlap between adjacent flight lines. Some notes about the scanning frequency. Scanning frequency is the number of pulses or beams emitted by the laser instrument in 1 second, and this is being measured in hertz. The older instruments emitted a few thousand pulses per second. Some of the earlier airborne LiDAR data that exists. The San Andreas Fault, for example, in the western United States, have a very, very low scanning frequency. Modern systems support frequencies of up to 1 megahertz, or even more than this now. The scanning frequency is important because this tells you how many points you collect per second, and that also allows you to make a flight planning. How high do you have to fly, and what is the expected point density that you reach on the surface? So a common older system operating at 150 kilohertz scanning frequency will produce twice as many points as a 75 kilohertz system. Common airborne LiDAR observations in European countries reach between 700 to 800 kilohertz, and usually a flight height 700 to 1,000 meters, sometimes even higher than this. It's not only about the scanning frequency, it's also about the type of mirror and system that you're using. Very often you just use a simple scanning mirror that is not changing any direction, and then you have a seesaw pattern. So if this is your flight direction, then the mirror is rotating and is just diverging the beam while you're moving forward. You can have different flight patterns that is smoothing those curves somewhat by using a different mirror setup. That's a stabilized seesaw. Sometimes you have parallel lines, and some rarely used mirrors end up in an elliptical path. What is important to realize that this mirror here for the most widely used pattern is not rotating in the same velocity, because if it's ending its turning point, it's slowing down because it has then to change the direction. So you actually end up getting a much higher point density here towards the end of the scan line. This is what you also then refer to. The points are bunching up because you're slowing down your mirror rotation while the scanning frequency or the laser pulse frequency, of course, remains the same. Okay. I would like to move on and give some examples of how you actually generate points. And I'm going to look at full waveform LiDAR data, because all LiDAR data are full waveform. And the points that we are ending up using is just a product that is being generated from the full waveform LiDAR data. But all LiDAR data are full waveform, but these are not always recorded. So let's think about this way. So you have an airplane, you emit a laser pulse that may be 8 to 10 nanoseconds long. That's your outgoing pulse, and that outgoing pulse is being returned, for example, at the ground. Then algorithms allow you to determine the peak of that returning function. For example, you place a point at the peak, and you have a point or you have turned your wave into a point, and this is what you end up using in your point cloud. A more complex example here with multiple returns going through vegetation indicates that you can have multiple returns every time a laser beam hits a branch or goes through a leaf. And every time this is above a certain threshold, you can place a point. So you turn that full waveform LiDAR data set here into a set of 4, 5, 6 points, depending on how many returns you have. If you are doing remote sensing of vegetation, you start to appreciate larger beam divergences, because they allow you to better penetrate through those vegetation. So let's look at some real data. This is a full waveform recorded signal of a ground surface here at the campus GOM at the University of Potsdam. The full waveform data has been recorded with 1 nanosecond sampling. That's a typical sampling frequency. So meaning every nanosecond you obtain a reading of your return signal. This is the original data here in blue. with the raw data not filtered. And the red line here indicates where the preparatory Regal algorithm has placed the point. So this is the point that you see in the point cloud, but this is the signal that the system is recording. So usually the first thing that you do if you want to turn a full waveform LiDAR signal into a point signal, you're removing background noise. That can be done by looking at the earlier points. That's essentially the background noise that you would like to remove because fitting is easier on such a denoised data set. And what you then end up doing is you want to determine the peak of that function because you are sampling with 1 nanosecond. You may not actually sample that peak of the function, so you are doing you fit a Gaussian signal. You fit a Gaussian signal, you're optimizing that fit until you have obtained the best fit, and the peak of that best fit usually gives you the point, and it also gives you the intensity of that signal because that's the full width half maximum integral of it. This is a very typical processing approach. If you end up processing your own full waveform LiDAR data, such as can be acquired from Neon or from other sites and providers, you can do much more with the full waveform LiDAR data. You can not only look at the intensity, which is essentially the height of this peak, you can also look at the width of this peak, and the width of this peak is a good material or property indicator, material indicator. And I'm showing you an example here of a larger building on campus GOM at the University of Potsdam, where we have collected multiple full waveform LiDAR data sets. Usually you end up fitting a Gaussian, and you then can also indicate the width of that fitted peak. So in other words, you can look at the standard deviation of that fitted peak. That tells you a lot about the material property. So for example, vegetation is scattering or returning much wider beams than the ground surfaces here. I also would like to point out that the fitting is not it's not always a Gaussian. That's not the best model. In fact, an exponential Gaussian fitting produces better results. We are not going into detail here. I'm just pointing out that if you end up working with billions of return signals, you may want to make sure that you're fitting a model that is best representative of the data. The nice thing about Neon data, for example, is that you obtain the outgoing waveform as well. So let's look at another example here with multiple returns. This is a beam that goes through a tree right next to a building, and this is the ground. And the colors here indicate the intensity as given from the full waveform LiDAR data. So you can envision that this is the first peak, the second peak, the third peak, and here is the ground peak. If we take that time, that is essentially the travel distance that we have here, and plot it, this is here the denoised signal already, we see the full waveform in blue, and we see the red lines here indicating the points that you end up having in the point cloud. This is again the proprietary algorithm that is employed by some companies by using a Gaussian fitting. And the reason why I'm showing this here is because I would like to point out that not every peak is nice and easy to fit, like this ground peak here, for example, but you also have much more complex peaks, and there you have a superposition of different Gaussians, and that makes it sometimes more complicated to identify a perfect fit. The same here, you probably would eyeball the peak of this function at a different position, but if you have two different Gaussians overlapping, you end up placing that point at a different location. So I'm showing this as an example that sometimes in dense vegetation cover, the points may not exactly placed at where you have the feature. It's just a superposition of different Gaussians that may be fitted. But the nice thing is when you look at those full waveform data, you actually can generate your own point cloud. By changing that threshold, by identifying more points that create features. So this is an example here of a single tree with a standard processing resulting in roughly 3,177 points using the standard processing as it is done from every data set that you end up using. You can change that you can change the processing and, for example, lower the threshold of points that are being returned. So this is a much denser point cloud that is being generated here from the full waveform LiDAR data, and the colors indicate actually the strength, the intensity of that signal. So this is a denser sampling that you end up generating, and you can make it even denser by generating much more points that are above certain thresholds that then would require additional filtering. Here you can also appreciate the scan direction that occurs, essentially how that tree is being scanned by the individual beams that penetrate through the vegetation. Okay. In this last part of this session, I would like to show some examples and applications, and I'm making the point again that this will be fairly short and condensed, but there should be time either in June or in the hour following that we discuss some of those points if you are interested in this. And of course, you can always send emails if there are some pertinent questions that you would like to have answered. And there are three things that I briefly would like to mention. One is using eigenvalue decomposition of point clouds that helps you to classify and segment data. We can do something similar with full waveform LiDAR data. That's where we then stack the full waveform into voxels. And I briefly mentioned that we can use point clouds to also perform flower routing, but that's something that will require a much more in-depth discussion and a separate presentation. Okay, eigenvalues. You have the opportunity with a dense point cloud to measure the direction of the neighborhood by using a matrix decomposition, and you can determine those eigenvalues, essentially the dominant direction that your neighborhood of points is pointing at. So if you envision that you have a point and you have 500 neighbors, and you end up determining the main directions of this point cloud. In other words, you're looking at the variances in different directions. So you can envision that you form an ellipse, and the ellipse has three orthogonal directions, lambda 1, lambda 2, and lambda 3, and these are the eigenvalues. You can generate those for individual points by using a KD tree as a neighborhood estimator, or you can generate this in a voxel neighborhood if you would like to have it in a somewhat more cube-like structures. The eigenvalue decomposition has been widely used in the previous analysis, but it's mostly relevant in urban remote sensing because you have nice scalar or planar features that can be identified. I'd like to show you an example here of the Castle Neues Palais in Potsdam, where you can clearly see that there is a building in the center of the image here that is surrounded by trees. So these are two different views. One is from more the top, one is from more towards the side. And I would like to draw your attention to the colors, because the colors show you that decomposition that has occurred, the eigenvalue decomposition. So this is calculated for 500 neighbors here. If the 500 neighbors do not have a dominant direction, if you envision that they look almost like a sphere, meaning that they all go in all directions, the 500 neighbors. You also call it the scattering component. These points are in red, and you clearly see that those vegetation points where the neighbors are not structured, not organized, are mostly in red. The green colors indicate the planar component, so where you have a very, very dominant direction in or where you have a very dominant direction in 2 dimensions. So essentially the XY plane is going white, and you don't have the orthogonal component. So these are very nicely to identify planar features such as the roof, but also such as the ground. So that's a nice way to classify your data set. And then we can also look, or we can also identify and distinguish linear features. Linear features are something where we have stick-like patterns. These are partly identified in trees. For example, branches could be, or trunks could be typical linear or stick-like features, but also parts of specific architectural features can also be linear features. So this is something that now could be used for a more sophisticated classification, and it also allows you to nicely assign additional attributes to your point cloud. This is something that we are going to explore in one of the lab exercises. We can do similar things with full waveform LiDAR data. And the idea here is to show quick examples of how we can aggregate full waveform LiDAR data without turning them into points. So without fitting Gaussians, just using the full waveform LiDAR data. And we're doing this for an example of the campus GOM, where we have a pulse duration of 8 nanoseconds. For that specific area, we have 3 overlapping flight paths. We have roughly 500,000 points. I'm sorry, we have 500,000 pulses. And we have 32 million waveform samples for this area. So the idea here is that we take the full waveform, and that we end up stacking the full waveform into voxels. And when you have a voxel, for example, half by half by half meter, and you have multiple waves going through there with a certain intensity, you end up stacking that signal. This has been previously described and has been applied to other urban data sets. And this is what something similar would look like for our area that we have been working in. So the colors indicate the intensity of the overlapping beams. These are the voxels. There is no there are no points used. Every individual sampled full part of the full waveform has been put into a voxel and has been added up. So the color represents the intensity within a voxel. And what we can do is we can use this voxelized data set here to again calculate a structural tensor. So we can use these data to determine the direction in the XY planar, or only in one direction, the linear features, or an isotropic or scattering, or more like ball feature that indicates no preferred direction. So this has been done here. This is a former master thesis that has applied these techniques. By the way, I did not do the color scale correctly here. The red is planar and green is linear. So these two labels here have to be changed. But what you clearly see is that we have a nice planar component here in red. That is a surface and also the roof. We have linear features that indicate stick-like features as facades of building, or here is a chimney, very nicely. And we clearly see that vegetation has a very different characteristics and can be classified as isotropic fairly easily. So these are very different than roofs and can be readily classified that way. So this is one way of distinguishing between roofs and vegetation cover. But again, we can dive into this in more detail at a separate discussion. Last but not least, I wanted to point out that you can also use point clouds to perform flow routing. This is specifically of interest to geomorphology or hydrology. And what we have been doing mostly is that we generate a DEM, a 1 meter DEM, for example, and then we end up flow routing the the surface water over this area. And the challenge with flow routing always is that you need to correct your DEM because you may have a bridge in there, or you may have some other artifact that does not allow for the water to flow downstream. So you're carving or you're breaching dams to allow water to flow downstream. You have the similar problems in point clouds, and the way this has been solved is by digging tunnels, by creating a network that connects the points. And if a point does not have a downstream neighbor, it can look into further, or it can look into a larger direction and then create a tunnel. So the idea here is to generate a facet flow-based network that does the flow routing. And if you end up having an end area where you would not find a lower lying neighbor, immediate neighbor, you can also enhance the search into a longer distance that then would allow you to create a tunnel. And you perform and you continue the flow routing. This is specifically of interest to areas where you have dense vegetation cover. These are two examples here. You see the red dots here indicating individual downstream particles or water particles in that sense that are migrating downstream. The color here is a specific catchment area, and this image here on the right hand side shows the near infrared lidar intensity, where you have the vegetation in dark colors and the bare soil in lighter colors. And this is where you would have no problems routing your flow through vegetation, because you can always be certain to find a downstream neighbor. But I'm very certain that Alyosha would be very happy to explain these things in much more detail in a discussion. Thank you.